Hello guys, it is me, and I'm here to teach you about stats. Um, yes, that's right, we're learning about stats today. This is gonna be you pretty soon because you'll be happy, because statistics is fun. So let's begin. First, we must start with the visuals. No, we're starting with something else. We're starting with um, a basic idea. Something called the population. What is the population? I spelled population wrong. Also, my P looks really bad. Let's go fix that because I want a quality production here. There we go. There's the P, H-I-O-N. The population is special. This is the group. This is the group of all your customers. This is all your viewers, all your neighbors, everyone. But you must choose what it is. It must be something specific. Maybe it's all the kids at a nearby high school. Maybe it's all the blades of grass. That's one. Blades of grass. Blades of grass in your lawn. Once you make a population, you can now start learning from it. But wait. What do you know about population? What we need something called a statistic. Well, really, it is statistics after all, but this is called a parameter. Parameter. Hold on. Yeah, it's a parameter. Parameter. A parameter is a type of statistic. What is a statistic? Well, I'm glad you asked. I can spell it. I can spell statistic. Great. Okay, so it's a kind of it's a number basically. It tells you about something. In this case, it's telling us about our entire population here. It's gonna parameter. Okay, so what's the most basic thing? We want to know. What do we know? Our grass. I know. What is our height? What's the height of the grass? Each grass. Now, if we took the careful care to measure every little thing of grass, we would realize something. We now have a distribution. We have a lot of information. We have this list, which is probably like long. Oh wow, it's 0.5 inches. Maybe this is 0.1 inches, so on and so forth. It's huge. And we want to see this list because a giant list of numbers is not very visual. It's not very pleasing. So let's pretend for a bit that you live in Los Angeles and your yard is about this big. Here's the house is like here's you. Hello. And it's super dry and you only have 5 blades of grass. There they are. Now if you measure each one, you'd realize that one blade of grass is 2 tenths of an inch. One is 0.35 tenths of an inch. Wait, no, 3.5 tenths. Another one is this, and then we have like maybe a tall one, it's 6, and then we have this really short one, 0.05. So the question is, how do you visualize this data? And this is where the humble graphs help us. We can learn this through a variety of measures. Let's start with the dot plot. Oh yes, this is classic. You all know this. I also wish I could draw straight lines. What is it? It's just a plot with dots. You can put dots there, and you stack them if there's more. So in this case, let's just pretend, use some imagination, pretend this grass grew overnight. And we see we have some data here. Let's arrange it, because arranging is fun and good. 0.1, 0.1, 0.2, 0.35, and 0.6. Great, all this data. Let's put it on a plot. I will increment, so it's going to be 0.1 here, 0.2, 0.3, 0.4, 0.5, and we'll put 0.6. We have all these values, and we start stacking dots. Here's 1, that's right here, that's you. I'll put the 2 ones in here. There's the 2. And we'll put the 3.5 kind of in between here, because why not? Great. Now we can see. Okay, I can see. Oh, here's something called a peak, a mode, if you will, where there's the most. It's unimodal. Actually, no, it's not unimodal. That's a lie. No, we'll talk about it later. In its mode, we have this appears, and we have all these kind of dots here, and we can visualize the data. So, if we went back to our beautiful lawn, which is not in Los Angeles, we would realize that maybe we have a lot of data, and we'd have a lot of dots. Now, it gets super tedious to kind of draw like 1,000 different data points, and that's where our humble histogram comes in. What is the histogram? Well, imagine this. Lots of dots here. What if instead of dots, it's a curve? Whoa. Now at any point, if we like say this is say 0.15 is the like that over there, and 0.3 or something. At any one value, we can go see how many dots, how many grass blades are on, well, technically, statistically, above it. There could, by the nature of statistics, be not a single blade of grass that tall, but out of the entire range, there should be one, if that makes sense. Anyway, this is a histogram, and it stores data. If we take a look at this, we see this histogram has one peak, it's one mode. Some histograms look like this, and boom, there's two of them, two modes. Wow, that's great. I wish we had a name for all of this, and we do. This is called a bimodal, because bi means two. I'm just splitting it for funsies, so you don't want to split it, you can just kind of not if you really want to. Bimodal. If it has one mode, it's unimodal. Amazing, right? Unimodal. And what's that? What if it has three modes? It's not three, it's four. Hold on a second. Let me remedy this. Boom, 3 modes. 1, 2, 3. Guess what it is? That's right. It's trimodal. Now it's time for the challenge question. Say we have this and its modals looking like this. This would be called a multimodal. I know, engaging. That's multiple, multi, got half the word. Modal. Now, before you comment, here's why it's called that. It's because there's multiple modes. See 1, 2, 3, 4, 5, 6. Even this multimodal can actually describe trimodal and bimodal, because guess what? There are multiple modes here. This is revolutionary. But first, while you bask in the glory of this naming convention, let me go drink some water. Water, delicious. That was truly delicious. Remember, kids, water is good for you, and you should drink it. Otherwise, you'll dehydrate. If you don't drink it, you'll last like, what is it, 3 days? I think it's 3 days or something before you die. It's the rule of threes, you know, 3 days, 3 weeks without food, 3 days without water, 3 minutes without oxygen, like, I don't know, 3 hours without shelter. Okay, so we have something called, this is called the beloved histogram. Yes, right, histogram. Now we have a graph of all the data. And if we go back to our beautiful parameter here, we want to know some of these parameters. Let's describe the data. Now, I know all what you're saying. Wait, but what about the average, the mean? And I'll say, good job, you're A students. Gold star. Congratulations. You have guessed next thing. So this is called the mean, right here. How do you write the mean? Like this, M-E-A-N. Amazing. But really, it's like this, mu. Now wait, it changes, but I'll tell you when that happens. So if it's a population, it's mu, and this is really supposed to be like this, I think. But I kind of just draw the feet long. Anyway, it's not an M. No, it's a U with lines. Mu. See? U. Yes, great. Okay, glad we agreed. So we could say, hey, our mu for this thing is, I don't know, 0.2, as we mentioned, not anywhere. Okay, yeah, 0.2, that's a parameter, that's a statistic. And now we know something about our population. Let's go calculate the mean by using some good old math. Now, I know what you guys can do with math. That's right. You can do it, I guess. Okay, here, you do it this way. You take all our values, which we'll call x. This is x. And we add it to each instance of itself. So we have 5, and at 1 plus x over, plus x1 plus x2 plus x3 plus x4. Boom, we have all 5 of them. I know I started 0. There's a reason for that, which you'll learn later. Ooh, I know, suspenseful. You divide by 5, because there's 5 of them. That's the average. So in this case, it's 0.1 plus 0.1 plus 0.2 plus 0.35 plus 0.6 over 5. This equals 0.234 0.95 plus 0.6, and then that leaves us with 1.55 over 5. Gorgeous. Now, let's do some division. Division. Fortunately, I did math when I was a wee lad. I know that it actually equals 0.31. Genius, yes, but you can thank me later. Let's get a 0 from this guy here. 0, gorgeous. Okay, this is the mean of our population here. Population mean is equal to 0.31. Does that make sense? Do you understand this? Now let's go back to this beautiful form here. What if we wanted to have a golden equation that you could use to be smart and show people or show off to other people and be like, ooh, yes. Well, let me introduce you to the summation. What is a summation? It looks like this. It's known, the symbol is known as sigma. Anyway, so what we have in a summation, we have a counter variable. So to break this apart, let's think about it. Here, boom, boom. Let's put this into each count. So it's x0 over 5 plus x to the 1 over 5 plus x to the 2 over 5, so on. You know how it goes. We just split this big fraction into small ones. And essentially, we want to have this variable, which we'll call n, which says n is the amount of terms we have. Here's n. So this has 1, 2, 3, 4, 5 terms. This means n equals 5. So if we rewrite this, this is going to be n. Hey, no, it's a 5, not n. You're cheating. N over x to the some number. This subscript here is going to increment. And that's where the magic is. So the summation is an incrementer. It goes from, let's call it k. K, boom. K equals 0 to, what should it go to? Let's make it go to 5. 5. And what it's going to do is, if we do x of k over 5, we'll leave out n for now. It's going to go like, okay, this is what it equals. Let me go erase this thing over here. It's kind of ugly. Equals, so it starts at 0, so x to 0 over 5. And then we increment, so k is now 1. This is plus x to the 1 over 5. Increment again, 2. X to 2 over 5. Increment, and so on and so forth, until we realize these are the same. Whoa, that's so cool. The summation is legendary. Now, as I said, n equals 5, and we want this denominator to change based on how much n we have. So we can rewrite our summation like this. K equals 0, and our upper limit is n, right? We want it to, this happens 5 times. If there's only 3 things here, we want to only happen 3 times, so that's where n controls it. X to the k over, and the denominator again is also n, because we want to divide by the number of items we have. N. And presto, this equals the mean. Wow. Also equals this. You'll learn about that later. Hold on. Patience, we're getting there. We're almost close. And like that, that is the mean. You found the mean for whatever it is. So that's how you calculate it. But if you have a large array like this, you'll need to use a calculator, because otherwise you won't go insane, because you'll have to be like, oh, let's just go add a billion things. Or use a calculator like this. But wait, I hear you say, but what is x of k? If you come from like normal math and whatever, you'll realize that it's usually f of something. F of x is equal to blah. If you have like, but most populations are not like actual functions. They're just lists of stuff, just a bunch of lists. What you essentially go through is be like, okay, here's list 1, and then list 1 is filled with x. So the first thing it is 0, 5, 2, 3, commas in between. Let's say it like this. So if we want to go x of 1, it's going to pick 0, 1. Boom, here it is. It's 5 equals 5. Presto. Beautiful, gorgeous. This is how this is working. And this is what these things use, because statistics doesn't usually run on functions. Well, we'll use functions later. So, population, we have this beautiful statistic here. Gorgeous. It's the mean. Let's learn something else called the standard deviation. Whoa, what's the symbol? That's right, it's sigma again. Ooh, it's everywhere, but it's actually lowercase. This, of course, is uppercase sigma. Okay, standard deviation. When we have a... Oh no, I forgot to tell you about something. Let's talk about the normal curve. Woo! Forget about the standard deviation for now. Normal curve is a special curve that looks like this. If only I could draw better. Maybe more like this or something, but that's just tiny. Yes, normal curve. Wow, it's so gorgeous. Normal curve has one thing. It has a value, the mean, and a standard deviation. Also, one thing special, another thing special, is that all the area underneath the curve is equal to 1. Whoa. Why? Because probability. Hypothetically, this means if you chose a random dot on this curve, like right here, boom, and since your mean splits the normal curve in half, that's a thing that only normal curves have sometimes, like, actually, no, it's for every curve. It splits in half. This means you have a 50% chance of getting, or 0.5 probability of, that's a dot is in here, and 0.5 that's on the other side of the mean. And that's how you do stuff. If we use an x value here, we could say x is equal to this. I don't know what it is, and then we could find the probability that it's on the left, lower than or greater than. This is a messy drawing. Wow. But that's normal curves. I know I explained this poorly. I hope you're holding on. I'm sorry. So let's let that sink in. Yes. Anyway, standard deviation, this thing here. It's essentially a measurement of how far from the mean is a certain variable on the normal curve. There's something, a rule which I can't remember the name of, which is like, oh, if you have a normal curve here, okay, no, we can't even pretend that one looks good. This one actually looks good. Let's get our line. Note, it actually never touches the line because there's always a chance that could be at the very end. But anyway, here's our mean. Let's draw our standard deviation. Boom, beautiful. Boom, beautiful. Okay, great. And there's only one more. So I know this is like 6s. I'm just kind of getting tired. The rule says that 68% of all of the normal curve is between these two, and I think it's 97.5%, I believe, is between these two, and the final two is like 98.9%. So if you need to find something one standard deviation away from the mean, that means that 68% of the data that's in this is where? That there. Yes. Does that make sense? All right, moving on to the next thing. We talked about populations. Populations. Right? Okay, great. Populations are everything. This is the everything you want to study. I'm like, oh, I want all the pixels on the screen right here. But I realize I can't actually like get all the pixels. That kind of sucks because that's a lot of counting. Look how small they are. They're so small. So what if I'm like, okay, I want to choose a few. I want a sample of pixels. Great. I'll take these here, these here, these here. Boom. And soon, instead of having a list that's like a bajillion terms long, I have a list that's like 5 terms long. 1, 2, 3, 4, 5. Perfect. Pretend this is a list that has some words in it, numbers. Why is this important? Because we can usually never in the real world get all the population's data. If you want to interview your customers, it's hard to get every single customer to, talk to you. You can only get some. You can only get a sample. And part of statistics, inferential statistics that is where we're making an inference, a guess, on what the population is like based on what our sample's like. The sample's always usually smaller than the population unless you're just getting the entire population. It should never be bigger. No, never bigger. Okay. Now, the sample has its own mean and standard deviation called X and S. Whoa, they look different. That's because they're different from the population one because they're fake. Well, they're not fake, but they're just for the sample. Now, one thing we must know about the sample is that we could potentially have a misguiding sample. If our sample distribution looks like this, and here's our mean, what if our real distribution looks like actually like this? This is the population distribution. Population, and this one's a sample. We've just been lied to. Oh no, here's the mean, but it's actually over here. This is bad. So, how do we alleviate this? Usually by taking a lot of samples. If you take 100 samples and say, I want all your means, and I'll graph it again on a histogram, that's right, it's like a, inception. We have a sample, that's a graph, it's really more like, and we take all the means, a statistic of the graph, and we put it in a different graph. Boom. So here's the means of all the samples. And if our sample's unbiased, which means it doesn't it's not wrong, it's not poorly taken, etc. That's a bad definition. Don't listen to me. The mean should be similar to, or should almost be identical to, the population mean. And it is by this that we find out the population mean. Yes, you have learned some things. Good. Do you understand now? Comprendo? Population, sample. Sample, the mean standard deviation from the exact same as the population. I never spoke to how to find standard deviation. That's outside the scope of this video. And that's all you're going to learn. Goodbye. Listen. Look, this is you. You're so happy now. You learned so much. Good job.